Good afternoon. Welcome to the Ninth Ave Annual Forensic Science Symposium virtual poster session. The name of this poster is Bloodstain Detection on Camouflage Clothing Using Machine Learning Analysis of Noisy Hyperspectral Imagery. My name is Nicholas Scott, and this work was done in collaboration with Sarah Jensen. I first would like to give an introduction. Military, law enforcement, and intelligence agencies are often tasked with forensic analysis-based operations in which there's a need to quickly assess the presence of wounds on bodies in remote positions. Hyperspectral imagery, a proven technology for the detection of anomalous substances in heterogeneous background environments, has seen use as a photonic detection tool for the wounded. This is mainly but not exclusively in the area of imagery of blood-stained clothing. Blood on clothing often appears in different configurations, which changes due to stresses that smear the fluid along the material. The ability to detect this modulation is important in assessing the versatility of HSI and multispectral imagery technology in detecting surface blood signs on a wounded body. Blood detection under conditions of smearing on camouflage cloth is explored using HSI and machine learning algorithms. Image segmentation for different blood smear conditions was performed using non-negative matrix factorization, competitive leaky learning, and Laplacian eigenmap-based anomaly detection. These are all machine learning algorithms. HSI characterization of bloodstains on clothing is the first step toward the creation of inexpensive multispectral imagery technology capable of performing remote sensing-based bloodstain image segmentation. The experimental setup is as follows. A 10-inch square digital camouflage cloth was placed inside a light diffuser box illuminated with a pseudo-sunlight spectrum light source, ensuring semi-Lambertian conditions. Spectral imagery measurements of the cloth with and without DARE blood smears were made using a Resonon Pika L hyperspectral imagery camera possessing a spectral bandwidth spanning 300 to 1050 nanometers. The camera head was 42 inches from the light diffuser box and was tilted downward from the horizontal at approximately 60 degrees. Average spectral profiles for the clean and bloodstained cloth look like this. Spectral amplitudes for bloodstained cloth are lower than for the clean cloth, which is to be expected since the reflectivity for clean cloth is much higher than for bloodstained cloth. Spectral signatures for both blood smeared cloth and clean cloth have distinctive peaks at 436 nanometers, 547 nanometers, 612 nanometers, and 709 nanometers, related to both the true physical reflectance of light off the cloth and a type of white light spectrum that was used in the experiment. Bloodstained cloth has small spectrum minima and maxima between 420 and 550 nanometers and between 620 and 700 nanometers. This is due to the bloodstained cloth photonic structure. And up here you can see basically the clean cloth has a much higher spectral profile, spectral amplitude than the bloodstained cloth. Shown here are the RGB images of the targets. In each target, going from left to right, you have increasing amounts of blood spares. So the total mass of blood in all the cloths are equal, but the amount of smearing increases as you go from target 1 to target 2 to target 3. 3 HSI cubes were taken of the blood smeared cloth targets, where each possessed increasing amounts of blood smear. Each HSI cube possessed 800 scan lines, where a single line had 900 pixels, and the rest of the HSI specs are shown below. You can read that at your leisure. The first machine learning algorithm that was used was non-negative matrix factorization, and shown here are basically slices of the non-negative matrix factorization for each of the different targets. Non-negative matrix factorization factors HSI into two different matrices, an NMF eigenvector matrix and an abundance or weight matrix. And basically, by using the eigenvectors, you can basically decompose the original image into these NMF imagery slices, which show image segmentation. The NMF analysis was able to segment blood-stained cloth and clean cloth for the first two talking conditions very robustly. You can see blood stains here and here in the first target, here, 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 and here, here, and here for the second target. But what's very interesting is that the image segmentation power decreases with the third. So there's a significant increase in image segmentation power here, where you can see faint signs of blood stains here and here, but it's not very crisp, or it's not as crisp as in target 1 or target 2. The second machine learning algorithm that was used in processing the HSI data was competitive leaky learning. Competitive leaky learning clustering is a neural network based algorithm where the similarity between input spectral signatures are calculated through numerical competition. With each iteration of the numerical algorithm, similar spectral signatures are placed in one of four groups, allowing for clustering of an image. So each of these pixels in this image are basically grouped into one of four different groups. By doing this grouping, you can segment or you can differentiate between the bloodstained cloth, which is shown here in the first target, and a camouflage cloth, which is shown here. CLL analysis was able to segment bloodstained cloth and clean cloth for the first two target conditions. There's a slight decrease in segmentation power on the third, but you can still see ample amounts or signs of blood segmentation, bloodstained cloth segmentation in target 3. So very crisp amounts of bloodstained segmentation power in targets 1 and 2. And you can still see some segmentation in 3, but it's not as robust as in target 1 and target 2. White boxes can be hacked out of these targets, which are used in the next algorithm, which is basically Laplacian eigenmaps. Laplacian eigenmaps are data-driven local structural preservation mapping that exhumes weak covariant structures in HSI data. A local window is used in conjunction with an eigenmodal method applied to a similarity graph to accentuate anomalous spatial structures, which are in this case the blood-stained cloth areas. Laplacian eigenmaps can robustly segregate blood stains and clean cloth using four Laplacian eigenfaces for the sub-images that were taken. So for this analysis, we can see that the blood stains are shown in red for each of the three targets, whereas the camouflage cloth is shown in yellow. And using Laplacian eigenfaces or eigenvectors, which come out of the algorithm, you can robustly differentiate between the blood-stained cloth and the camouflage cloth, especially in target 1 and target 2, and even in target 3. As the blood stains spread in surface area, image segmentation power for some of the algorithms decreases, causing confusion between the camouflage cloth pattern and blood stains. Can this confusion trend be quantified? And the answer is yes. The Kullback-Leibler divergence and the Bhattacharya distance, which are both distance metrics sensitive to covariance, were calculated as a measure of the distance between clean cloth and bloodstained cloth. Large distance values indicate strong separation of clean cloth and bloodstained cloth areas. And so these are basically the Kullback-Leibler divergence and the Bhattacharya distance. What you can see is that the distance metrics are large when the blood smearing was small. That means when you have little blood smearing, which is what you would expect. which is shown here basically on this axis, and the distance metrics were large when small numbers of principal components were used, where the principal components are used which is shown on this axis. Basically, the principal components are just simply the spectral bands that you have in the HSI data. What you can see is that there's a peak in the Kullback-Leibler divergence and about a charge distance at very small PC numbers and very small blood smearing values. So in conclusion, what we've learned from the distance metrics is that HSI blood stain detection using machine learning analysis is possible, but its efficacy decreases as blood stain smear increases in surface area. It makes sense. If a soldier or a law enforcement person, whether he's part of SWAT or whatever agency, is wounded, as the person rolls, if he has a wound on his uniform, as the person rolls and increases the blood smear, the ability to detect it on the uniform gets smaller. What's good for us is that small PC numbers are associated with high value distance metrics, which suggests that the MSI technology for blood smear detection is possible, since this detection only uses a small number of spectral bands. We saw previously that we had a peak in the distance metrics when you have a small number of PC numbers. Well, MSI technologies is also based on a small number of spectral bands. So the ability to basically pull out information using a small amount of PC numbers is actually good for what we're trying to do and what we would hope for in the future. Again, to recap, I'm showing an image of the full poster as it was created. The points are that HSI blood stain detection efficacy decreases as blood stain smear surface area increases. The distance metric suggests that MSI tech for blood smear detection is possible. The future goal is field-ready MSI sensing capability for blood stain assessment for quick scene characterization and evaluation. Again, we're looking to basically produce in the future a camera that can really help law enforcement and the military identify blood stains on the wounded quickly and efficiently in the field. My email is at the bottom, nscott@riversideresearch.org. If there's any questions, please feel free to contact me. Thank you for listening.